So good morning or good afternoon, good evening, wherever you are joining us from, anywhere in the world. My name is Alberto Di Meglio. I'm the coordinator of the CERN Quantum Technology Initiative, or CERN QTI here at CERN. The CERN QTI has been recently formed to support the high-energy physics community in assessing the state-of-the-art, the potential of quantum technologies in applications to physics and related sciences. And of course, to support the community in contributing to the further development of these technologies, alongside with the many international initiatives that are working on quantum. Now, given the fast evolution of these technologies and in a way the complexity, we think it is important to dedicate time to developing not only the technologies themselves, but also knowledge and education. So in the most, if you want, traditional CERN way and HEP way, we want to do it in a very collaborative and inclusive way. So that's why we start today with this first lecture. This lecture is the first in a series of lectures provided as an introduction to quantum computing. The lecturer is Elias Combarro. Elias is an associate professor of mathematics at the University of Oviedo in Spain and scientific cooperation associate at CERN in CERN Open Lab. This is also the first in a series of educational and training initiatives that we are going to organize in the coming months, covering all the four main areas of quantum technologies: computing, sensing, communications, and more theoretical aspects of information processing and quantum simulation. So I warmly welcome you to this first introduction. If you have comments or suggestions for this kind of initiatives or in general quantum technologies, please do not hesitate to get in touch and work with us to make these successful initiatives. So welcome again. Elias, the stage is yours. Thank you.
Thank you very much, Alberto, for the introduction. Thank you also to all the people behind the CERN Quantum Technology Initiative for arranging these lectures. Thank you all the people that have been organizing all the details for these lectures to happen, the people that have been taking care of the webcast, of the Zoom meeting that we are having here, of organizing the Indico page, of publicizing the event. I know that it has been a lot of work. They have been working very, very hard, and if not for their effort, this could not happen. So thank you to all. Also, thank you to all the people that are joining us, either at the Zoom call, at the Zoom meeting, or via the webcast, or those people that are watching the recording that we are going to publish a few days after this lecture. Welcome, everybody. I've seen that there is a lot of interest. I've received a lot of messages from people all over the world asking about these lectures. So I'm really, really happy that that there is this interest in quantum computing. This is a field I really I'm passionate about, and I really hope to share part of this passion that I feel with you during these lectures. This is really a pleasure and an honor for me because, well, I remember that exactly 2 years ago, here at CERN, it was taking place a workshop on quantum computing for high energy physics. And at that moment, I could not make it in person. I could not attend live the sessions, but I could follow many of them through the webcast. And well, I could not imagine that 2 years after that, I would be able to participate, to humbly contribute to this really interesting effort, this really interesting initiative in quantum technologies that is taking place at CERN. So thank you, everybody. Thank you for your interest, and welcome to these lectures. Let me remind you a little bit what is the structure of the course. As Alberto has mentioned, we have 7 lectures, and they will take place from 10:30 to 12:30 every Friday at Geneva time, which is, I think, a Central European time. And they will be recorded. There will be also the live webcast that most of you or many of you are watching now. And also my slides and some of the code that we will be using during the course and some useful links will be available in the Indico page that you have probably visited in order to enter the webcast. At that page, we will also publish the link to the video of the recording of the session once that it is available. One thing that it's important, or that I want to warn you about, is that in the webcast, not in the recording, but in the webcast, I've been told that it is possible that my webcam, the picture-in-picture with my webcam, sometimes can cover part of the screen. Okay, so if you want to read all of the text in the slide, sometimes maybe my face will be on top of that. So you can download the slides and then follow everything from those slides without my face in front of that. Okay. I also want to especially welcome the people at the Zoom meeting. You know that we have organized this with an interactive part. Some people have been invited to this Zoom meeting, and they will be able to ask questions and to interact with me. And this is something that I really ask you to do. Do not hesitate to interrupt me. We were commenting before starting the session that it's really hard for us teachers. I've been teaching now for 20 years live in front of an audience, and I really miss seeing the face of the people and feeling whether my message is getting through or not. Back in the first lockdown in Oviedo, I had to teach also online for 2 or 3 months, and it was really something hard. It's a weird feeling to be on your own on an office talking to a screen for 2 hours, and it really is very, very different from live teaching. Okay, so please do not hesitate to interrupt. I will now look for the chat because I think it's not, I don't have the window, but now I have the window here. I will be able to read your messages, your questions. You also have the opportunity of raising your hand with the option at the Zoom client. And please feel free to give feedback, to interrupt when there is something that is not clear, or if you want me to elaborate on something. Okay. I think that is all. Well, people who are watching the webcast or the recorded sessions can also send me questions if they have doubts to the email. You can see my email now on the screen. Of course, I think that there will be quite a lot of people watching these lectures. Of course, I don't promise that I will be able to read all the email or to answer all the questions, but I will try at least to select some of the questions that I received. And at the beginning of the next session, I can answer those questions if I see that there is something that was not clear that many people are asking. Okay, so feel free to contact me with your doubts, with your questions, and also I could somehow accommodate topics that you want me to cover. I will explain in a minute what is prepared or what I have selected as topics for the course, but there is some slack to move things or to accommodate things that you can be interested in. And I think that is all about the schedule of the lectures. So let me start with the content for today. So today the first part will be, of course, an introduction to what is quantum computing. So all of us have read many stories in the papers, have read many articles in the news, or watch in the TV announcements about quantum computing, and this is something that is now a very hot topic. So please let me start by reminding you one of the biggest announcements, if not the biggest of them all in quantum computing in recent time. A little bit more than 1 year ago, exactly on the 23rd of October 2019, Google officially announced that they had reached what it's called quantum supremacy. So we will devote time to explain what is quantum supremacy, what Google exactly did in order to achieve this quantum supremacy. This will be probably on the last lecture of the series. But for now, let me explain briefly what is this quantum supremacy. Okay, so what Google announced is that they have been able to run a certain task. The details of this task are not important as of now. We will talk about them as I've told you in the last lecture, but they have been able to run a certain computational task in a quantum computer in a very short time. They mentioned a time which was about 200 seconds, little more than 3 minutes. And they estimated that running this same task, even in the biggest supercomputer, classical supercomputer in the world, would take thousands of years. Okay, so wow, this is something that is shocking. There has been some debate about whether this figure of thousands of years is really correct or not. We will discuss this also on the last lecture. But of course, this difference of orders of magnitude in computing something, of doing some computational task in a quantum computer and in a classical computer is shocking for anybody that is interested in science or in technology. This is something that is at least very, very intriguing. And for people like us who work with computers for our research or for our business or for whatever kind of computational task we want to conduct, this is really a very, very interesting situation, because now it seems that we have these quantum computers, these mysterious new tools that are able to at least perform some computational task in a much faster way than classical computers, okay? So the natural question here is, well, what are these quantum computers? What can they do for real? And in particular, for any of us here at CERN, for high energy physics problems and computations, the question is whether we can use these quantum computers to get some advantage, to make our computations faster, or to reduce the kind of resources that we need for our computations in some way. For instance, reducing the memory or reducing the amount of data that we need in order to reach some models or some conclusions. Okay, so this is, of course, a very intriguing question. What can these computers do? And unfortunately, this is a question that is very, very difficult to answer. And it is difficult to answer for two main reasons. The first main reason is that mathematically, we don't really understand fully what are the capabilities of quantum computers. We have a good theory, a good definition of what a quantum computer is. In fact, several different definitions. I will tell you about them in a few minutes. But we cannot prove mathematically even that there is at least one task in which quantum supremacy seems to indicate the opposite, that we know that quantum computers are faster or more powerful in some sense. So in fact, in some sense, we will task during the lectures, but we have not been able to prove this mathematically. The problems these quantum computers, although we strongly suspect that quantum computers are more powerful for some tasks. So this is the first reason. We cannot prove mathematically yet that quantum computers are faster. But also there is a problem from the practical point of view. Well, maybe we don't have the possibility yet of proving this mathematically beyond any kind of doubt, but at least we could, like Google did, try some tasks and see whether quantum computers are, in practice, in real life, faster than classical computers. The problem with this different approach, this practical approach, is that limited and prone to noise and to errors. We will talk being able to reach this quantum supremacy, to achieve this quantum supremacy. It was really a very, very difficult task of engineering, of tuning the systems, and also of selecting a with some practical computational problem, with some practical task, that quantum computers are faster and are useful now. And this is something that probably in the medium term, or even in the near term, we will be able to show. But as of now, we have not been able to run a practical computational task in which quantum computers are better than classical computers. Okay, so my goal here with these lectures is to provide you with tools, with concepts, with ideas, in order for you to also explore these possibilities. Okay, many of you work in high energy physics or in other fields of research or business in which you require lots of computation. So what I want here to show you in these lectures is what quantum computing can offer you, what are the possibilities, although we are not yet sure of which of those possibilities are going to prove true. So you can explore further what quantum computing can make for you, okay? And with this goal in mind, the philosophy of the course, it's a very practical one. You've seen that the title of the course is a practical introduction to quantum computing. Okay, so of course, first, let me stress that this is a completely introductory course. Some of you may know already many things or some things about quantum computing, but I don't expect you to know anything about quantum computing or quantum physics at all. Okay, I will introduce from scratch all the concepts that we need, and I don't expect you to have any previous knowledge. Of course, if you have this knowledge, it will help you, and it will give you some intuition, although you know that intuition and quantum mechanics don't get along that very well, but all your background, of course, will be helpful, but I don't expect you to have any previous knowledge. The only thing that I assume that you know is linear algebra. Linear algebra, as you will see, is the main instrument, or it's 90% of the mathematics that we will use to study quantum computing, and I assume a good command of linear algebra in order to follow the lectures, but that is all, okay? And the other aspect, the other part of the title that I want to stress is the practical part. There are many textbooks on quantum computing. There are many courses on quantum computing, but sometimes I feel that they lack this practical orientation. Okay, to me, quantum computing is, of course, the intersection of many different fields. Of course, it's the intersection of quantum mechanics, of computer science, of mathematics, of statistics, of engineering in the part that has to do with the construction of quantum computers. But at the end of the day, I cannot help feeling that quantum computing has to be overall about computing. Okay, if quantum computing is going to be practical in the future, it has to be about doing computations, about being able to run algorithms on computers. Okay, so I have taken the liberty, with all due respect to the great Albert Einstein, to somehow modify this sentence that is attributed to Einstein. He's supposed to have said that if you can't explain something to a 6-year-old, then you don't understand it yourself. And I have changed the 6-year-old for a computer. Okay, so to me, in quantum computing, if you can't explain the algorithm, the protocol that you are studying or implementing or developing to a computer, then at the end of the day, it's not useful, because at the end of the day, you want to execute your algorithm in a computer. Okay, so my focus will be overall on going to the implementation. Okay, on showing you how to program a quantum computer. And since the focus will be on the computational part of quantum computing, I will have to skip a little bit the other parts. So I won't explain much about quantum mechanics or about mathematics, although I will try to, as also Albert Einstein said, to make it as simple as possible, but not simpler than that. Okay, so I will explain all the concepts that we need in order to understand the algorithms. But what I want is to stress the importance, the relevance of being able to program the quantum computer. Okay, so for all the protocols and algorithms that we will be studying, I will tell you about them in a minute. I will provide at least one implementation. In the first protocols, it will be very simple, because it will be just a simple circuit. We will be talking a lot about quantum circuits in these lectures. And in more advanced algorithms, probably I won't be able to show you the complete code, but in all the cases, I will point you to implementations in different frameworks, in different libraries that we are going to use. I will also tell you about them in a minute. So you can, on your own, explore these implementations and check all the details that I will be explaining from the theoretical point of view to see how they are implemented in practice. Okay, and in all the cases, we will be executing examples of these algorithms and these protocols. Not in all cases we will be able to run very complicated cases. In some situations, we will have to simplify the algorithms or run them only in very simple cases, because of the reason I was telling you about earlier. That is one of the problems with showing that quantum computers are more powerful than classical machines. And this is that we don't have yet very powerful or very robust quantum computers. But in all the cases, we will at least execute something in a simulator, in a quantum computer, for you to check. Okay? So what are the tools that we are going to use in order to implement these algorithms and run these algorithms in quantum computers and in simulators? Well, we will use mainly the Python programming language. I confess that this is not my favorite programming language by any means, but is without a doubt the most popular among the quantum computing community. And almost all or most of the frameworks and libraries that are implemented for quantum computing use Python. Okay, And to run this Python code, well, if you have some knowledge of Python, it will be helpful, but also you will see that the programs that we will be running are not really very complex from the Python point of view, from the classical algorithmic point of view. We will focus more on the quantum part, okay? So it's okay also if you have not experience with Python. I think you will be able to understand the code quite easily, okay? And to run these Python programs, we will use Jupyter notebooks. I'm sure that all of you or most of you are familiar with Jupyter notebooks, but let me remind you that these are web applications in which we can combine code, in this case in Python, but we can use other programming languages, in our case Python, code, images, formulas, text, and we can make this interactive. So we can change little details in the code, we can change parameters, we can change the data, and then run immediately the code to see the new results, okay? So this is really, although I don't really like Python that much, I love Jupyter notebooks. They are very helpful, especially for courses like this, because it's very easy to show how a little modification in the code can lead to different results, and it's very dynamic, so to say, okay? Of course, many of you will already have Jupyter notebooks installed on your laptops or desktops. If not, you can easily install, for instance, Anaconda to have the Jupyter server, but this is not needed. This is not needed. In fact, you won't need to install anything because we will be using the cloud for all our computations, okay? And for instance, to run Jupyter notebooks, you have many different options. You have mybinder.org, you have Google Colab, you have other platforms, but we will be using mainly the Jupyter server that is included in the IBM Quantum Experience. The IBM Quantum Experience is the main platform that we are going to use in order to write our programs and to run our programs on quantum simulators and actual quantum computers. This is a platform released by IBM back in 2016. It's free, it's public. You can sign up following this link. There is also the link on the Indico page. And in the second part of the lecture, we will indeed sign up to this cloud platform, and we will start using it to run our quantum circuits. Okay, so if you want to get a head start and sign up now, you can do it. If not, I will give you some time to sign up during the second part of the lecture. It's really easy. You only need to provide your email address and some other data, and for free you will be allowed to use both quantum simulators and actual quantum computers. And this is, I think, very interesting. Okay, here I want to mention the difference between running a program in a quantum simulator and on an actual quantum computer. I think it is more or less clear. But of course, when we run a program in a quantum simulator, we are not running it on actual quantum hardware, on an actual quantum device. It's a simulation of the behavior of a quantum computer in a classical computer. And we can do this up to a certain number of qubits. We will talk about qubits, of course, a lot during the lectures, and we will introduce the mathematical concept later today. But when the number of qubits in the circuit that we want to run grows, the complexity of the simulation grows exponentially. So it is only possible to run these simulations on the classical computer up to some point. With the quantum simulator provided by the IBM Quantum Experience, we can run up to 32 qubits, okay, which is quite a lot for the type of circuits and algorithms that we are going to run is more than enough. But we also will have the opportunity to run some of these circuits, some of these algorithms on actual quantum devices. In the free account that you get with the IBM Quantum Experience, you will have access to quantum computers with 1, 5, a lot with 5, I think just one which has 1 qubit, a lot, 6 or 7 at least, which have 5 qubits, and then one that has 15 qubits. Okay, so we have some good opportunities to run our programs in a quantum computer, and we will do it. My goal is to do it at least for a simple circuit by the end of the lecture. Okay. These quantum computers have different connectivities, different topologies. We will see what this means. And it is all sometimes useful to try your program in different quantum computers because they also have different calibrations, different levels of error, and you can obtain different results. We will talk about all this. Okay. And the good thing about the IBM Quantum Experience is that, as I've mentioned, you can run directly your Jupyter notebooks on the cloud. Okay, this is a feature that was included on the IBM Quantum Experience earlier this year. I think, yeah, it was in 2020, and it's really very convenient because you can just upload your notebooks or create a new notebook on the platform and run it there on the quantum simulator, or changing a few lines. We will see soon how to do that, run it on the actual hardware. Other resources that we are going to use are an online simulator of quantum computers, which is called, or quantum circuits, that is called QUIRC, which has been called by some the most beautiful quantum simulator ever. Okay, and I tend to agree because this is a very useful tool. It has a lot of different gates. We will talk later about what quantum gates are. And it also has a lot of visualization options. And it's very helpful when you are trying to understand a circuit or developing a new quantum circuit, to just simulate it on QUIRC, which is an online application that you can run directly on your browser, and see what is going on inside the circuit. You have many options to see what are the states of the qubits and what is happening with the gates that you are adding. Okay, here you have the link. You also have the link on the Indico page for this lecture. Okay, and finally we will also use what is called D-Wave Leap, which is similar to the IBM Quantum Experience. It's provided by a Canadian company called D-Wave, which commercialize quantum computers of a certain kind, which are called quantum leaders. And it is possible to access these quantum computers, or at least one of them. I don't know if now they were talking about adding a second one. I don't know if it is ready yet. Or it will be in the near future. And it is possible, again, to access for free this quantum computer and execute some programs there. These quantum computers are different. Maybe you have heard about D-Wave quantum computers, and you have read news saying that, well, D-Wave has constructed a quantum computer with 2,000 qubits or 4,000 qubits. And we were talking here about quantum computers from IBM with 1, 5, 15. So why this difference? Well, the difference is that the quantum computers that D-Wave builds are not general or universal quantum computers. They cannot execute any quantum program. They are thought to solve certain kind of problems. They are thought to solve what we call quadratic unconstrained binary optimization problems, or minimization of energy in the Ising model, which is something that the physicists in the audience, of course, will know. And these are useful because they can be used for approximating solutions of very complicated optimization problems, but are not universal quantum computers. They cannot run any kind of algorithm, but these particular cases. Okay, so this is something that we will learn how to use the theory behind this way of doing quantum computation, and how to use the quantum computers at the D-Wave Leap cloud platform, I think in the 5th lecture. Okay, so these are more or less the tools that we are going to use. And with these tools, we are going to study a number of different algorithms and protocols. Okay, it was of course difficult to select what to include in the course and what not to include in the course. This is an introduction. We have only 7 lectures of 2 hours. Of course, it's impossible to cover all the different quantum algorithms or all the different possibilities that quantum computing and quantum information processing have to offer. Okay, so I tried to select some of the more representative and also some of the more modern ones, or some of the ones that in the late years have been proposed in order to solve practical problems with the kind of computers that we have today. Okay, so we will start somehow chronologically, and we will increase the complexity of the systems that we are going to use, and we will follow more or less the historical development of quantum computing, more or less. And today we will focus on the basics of what is a quantum circuit, what is a qubit, what is a quantum gate, and all that. But next week we will start studying already some interesting and useful quantum algorithms and protocols. And we will start first with just 1 qubit. And you may think that, well, 1 qubit is not that much, but it's surprising that with 1 qubit we can do some very, very interesting things, and some things that seem to be not possible with classical computers. Okay, in particular, we will use the property of superposition, and also the uncertainty principle, the impossibility of distinguishing 2 quantum states in certain situations, to talk about a way of doing what is sometimes called quantum cryptography, and what probably should be more appropriately called quantum key distribution. Okay, this is the famous BB84 protocol that allows 2 people which are far away to share a secret key that then they can use to communicate over a classical channel that is not secure. Okay, so this is a very, very interesting protocol, one of the first developments in quantum information processing. And we will see how superposition and the uncertainty principle is really the key here. Okay, so this is one of the first properties that we will see that come from quantum mechanics that allows us to do some information processing in a different way. Then we will see some modifications of this protocol and other protocols that also use only one qubit, okay, which are also interesting. And then we will move on to systems with 2 qubits, okay? And when we move to systems of 2 qubits, we have a new possibility, a new property of quantum systems that we can use to make quantum computation and to make quantum information processing. And this is the famous entanglement property. Okay, so we will talk a lot about entanglement and what it means for quantum computing and for quantum communication and for quantum information processing. And as a particular example, I have selected this CHSH game, which is a game proposed to test or that can be used to test whether nature is really quantum or is classical. And we will run a very simple experiment on the quantum computers on the IBM Quantum Experience to check whether nature is quantum or classical. Spoiler alert, it is quantum, okay? It is quantum. But we will check this with the IBM Quantum Experience. Of course, this is not a serious experiment or loophole-free experiment, but at least it will give us a taste of what is special about entanglement and what is the difference between doing computation with these new properties that quantum mechanics has to offer. Okay. Then we will also study, probably on the third lecture of the series, some other protocols which are based on entanglement, which are the famous quantum teleportation, in which we will be able to teleport information from one qubit to another, even if they are very, very far apart. And we will also study something that sometimes is considered like the inverse of teleportation, which is super dense coding, okay, in which we will use quantum bits in order to send more information than what we are supposed to, okay? And in these protocols, in the CHSH game, in the quantum teleportation, in the super dense coding, we will use entanglement extensively. But arguably, up to this point, we won't be dealing exactly with quantum algorithms. All these are, you may call, quantum communication protocols, but we still would not have seen a real quantum algorithm. And after seeing the properties of superposition and quantum entanglement, we will be able to introduce the third important property of quantum systems that will help us in doing quantum computations. And this is interference. And we will introduce this property by means of studying what is probably the first quantum algorithm ever proposed, which is Deutsch's algorithm. Okay, and you will see that this is an algorithm that solves a problem that is really not very interesting in practical situations, but it will show how quantum computers have some possibilities of surpassing classical computers in some situations. And for this, interference will be paramount. Okay. After this, we will graduate to multi-qubit systems. Up to this point, we will be working only with 1 and 2 qubit systems, and we will be starting to study what happens when we have many qubits. And here, when we have many qubits, we will be studying what happens with the famous quantum parallelism, okay? And how can we use this in useful computations with some algorithms. We will study the generalization of Deutsch algorithm, which is called the Deutsch-Jozsa algorithm, which again is not very useful in practice, but shows some of the possibilities of using quantum computers to perform tasks in a faster way. And then we will use 2 of the more famous quantum algorithms ever. Grover's algorithm, which is probably my favorite or one of my favorites, which is used to accelerate search in unordered structures. Okay, and this is a very, very interesting primitive for other quantum algorithms as well. And the most famous of them all, Shor's algorithm, which, as you probably know, can be used to factor integers, and then has serious consequences for some of the cryptographic protocols that we use currently on our transactions on lines and whenever we want to exchange private information, okay? And we will study Shor's algorithm from different points of view. We will study what the quantum Fourier transform has to do with the possibility of factoring these integers. And we will also study how Shor's algorithm is a particular case of the quantum phase estimation algorithm, which is something that can be used also for other kinds of computations, okay? For instance, the famous HHL algorithm that can be used under certain circumstances to solve linear systems of linear equations in a time that is exponentially faster than with a classical computer. This will cover, I expect to finish this by the 4th lecture, and this will cover more or less what is sometimes considered the canon of quantum computing, okay? If you take a look at some of the most famous textbooks in quantum computing, you will see many of these algorithms explained there, together with others like Bernstein-Basirani or Simon's algorithm, okay? And after this, I want to move on and to show you some more modern algorithms that now have been proposed, most of them in the last few years, to tackle optimization problems and to tackle also problems in machine learning, for instance, okay? And here is where we will be able to show some applications that some research groups all over the world in high energy physics are starting to develop in order to study how quantum computers can be helpful for particle physics, okay? So we will devote a whole lecture to optimization algorithms, including the quantum annealing way of computing that I told you about, that we will try with D-Wave's quantum computers. Also the famous QAOA quantum approximate optimization algorithm, which is a particular case of another very interesting algorithm, which is called the variational quantum eigensolver. And we will see how this variational quantum eigensolver can be used to approximate the ground states of chemical and physical systems, okay? And I will show you how this algorithm can be used in these situations in which you have to find the state of lowest energy of a system given a Hamiltonian, okay? And I will show you how this is at least starting to be used in projects for useful computations, both in chemistry and in physics. In the 6th lecture, we will study the marriage between quantum computing and machine learning, what is called quantum machine learning. We will study different models of quantum machine learning. We will study how some of the algorithms that we have studied in previous lectures, like for instance, the quantum Fourier transform or the variational quantum eigensolver, can be used to accelerate some processes in classical ways of doing machine learning. But I will focus mainly on the possibility of using quantum computing in a new way, to have more expressibility and to develop algorithms that are purely quantum in some way, while retaining the essence of machine learning. And here I will show many different examples of how these algorithms can be used in tasks in high energy physics, especially because many research groups all over the world are working on this. People here at the CERN Open Lab are working on this, collaborating with other groups, and there are some preliminary results which I think are very, very interesting, okay? And the final lecture will be, we'll try to wrap up all what we have learned during the course. We will talk about what we can expect in the future for quantum computing. And then we will talk about something that, of course, we will mention during the other lectures, but we will not explore very, very deeply. But in the last lecture, we will talk about quantum error correction, something that prevents the computers that we have today, the quantum computers that we have today, to perform useful tasks, is the problem of errors, the problems of noise. And if we expect to be able to run algorithms like Shor's algorithm or like Grover's algorithm, we need computers that are robust against noise, what we call quantum computers with complete fault tolerance, okay? And we will talk a little bit, because this is, of course, a topic that could encompass the whole course and more. We will talk a little bit about how we can perform error correction in quantum computers, okay? And we will also talk about the famous quantum supremacy achieved by Google. We will explain what is the concrete task that they did, what is the relation of doing this task with quantum simulation, and we will also explore a little bit what we can expect in the future. What are the plans of some companies for releasing new computers with new capabilities or with more bigger number of qubits, and what we can expect from quantum computing in the short term. I don't know if there is any question about this or any suggestion. Okay, so let me remind you, things that are important in the protocols that I have mentioned are superposition, for instance, for quantum key distribution, entanglement for quantum teleportation, for instance, interference for many of the quantum algorithms that we will be studying, okay? So these are things that are characteristic from quantum computing. And this is what leads us to this definition, finally, of what is quantum computing. Quantum computing can be defined as the computing paradigm that exploits explicitly quantum mechanical properties of matter, such as superposition, entanglement, interference, to do calculations. And well, you can argue that even the classical computers that we use today use properties from quantum mechanics. Of course, the semiconductors and the transistors that are in the processors of our computers use properties from quantum mechanics. But the difference with quantum computing is that we explicitly use these properties to do computations in a different way. Many people think that quantum computers are just faster computers that, because they work with maybe particles which are subatomic, can do computations faster in the same way that whenever we reduce the size of our microprocessors, we can do computations faster. Well, this is not the case. A quantum computer is not a faster computer. Quantum computer is a computer that does things in a different way. Okay, so we could say that we are not in Kansas anymore. We are in a different country. And we need a new definition of what is computation, okay? Many of you will know about the famous model of classical computation, which is called Turing machines. There are many different equivalent ways of defining the capabilities of a classical computer, but probably Turing machines is the most popular of them all. And we can define by analogy, this was done by David Deutsch back in the 1980s, what we call a quantum Turing machine, okay? And this is a different model of computation that explicitly uses quantum properties like entanglement, interference, superposition, okay? This is a theoretical model. This is not very practical. This was, I think, the first quantum computational model that was proposed. And we will work with a different model that is computationally equivalent, which is the model of quantum circuits. Okay, there are many other different models, as in classical computing. You have the measurement-based quantum computing, adiabatic quantum computing, topological quantum computing, counterfactual quantum computing. There are many different ways of doing quantum computations, but the most popular of them all is, without any doubt, the model of quantum circuits. And all the quantum computers that we are going to use, well, at least the ones in the IBM Quantum Experience and the ones that Google used to achieve quantum supremacy, are based on this model of quantum circuits, okay? And if one studies these models of computation, it is easy to show that, in fact, these models in the sense of what functions can be computed are no different from classical computation. So, for instance, there is no possibility to solve problems with quantum computers that cannot be solved given enough time and given enough memory with classical computers. Okay, for instance, the famous halting problem that is not solvable with Turing machines is either unsolvable with quantum Turing machines. So the difference is not in the functions that we can compute, but on the resources that we need to compute these functions. Okay, so the idea then is to explore what are the resources needed by the different models, the computational, the quantum computing models and the classical models. And here I'm showing you a very simplified picture of different classes of problems that we can tackle with quantum and classical computers. Okay, I don't want to go into much detail about the different definitions of these classes. Probably many of you know about some of these classes, but let me remind you that the class of P problems are those is the class of those, the set of those problems that we can solve efficiently with a classical deterministic computer. While the class of NP problems is the class of those problems that we can check, we can verify a solution efficiently with a classical computer. Okay, so the big question in classical computational complexity is, of course, whether P is equal to NP or not. Okay, in fact, this is the 1 million question, literally. The Clay Mathematical Institute offers, this is one of their millennium problems, offers $1 million to the person capable of solving this problem. And we strongly suspect, we have strong evidence that P is not equal to NP. That is not the same to find the solution to a problem, that is what we can do in P, than to verify a given solution to a problem. That should be much easier. That is what we do in NP, but we are not able to find the solution. But we are given the solution, then we can, with a classical computer, certify that this is a solution. Okay. Then we have the P space problems, which are the problems that we can solve in a classical computer given polynomial memory. Polynomial meaning that the amount of memory that we need grows polynomially with the size of the input. Okay, and we know for sure that P is included in MP and MP is included in P space. Okay, and we suspect that P is not equal to MP, that are problems in MP, in particular the problems that are called MP complete that are not in P, and that there are problems in P space that are not included in MP, but we have not been able yet to mathematically prove this. Okay, to complicate the picture, now we have the problems that we can solve efficiently with a quantum computer, and this is what we call the class BQP, bounded quantum polynomial time. Okay, and this is the class of problems that with a quantum computer we can solve probabilistically. Okay, here the B stands for bounded error. I won't go into the details, but we need to take into account that the model of quantum computing is a probabilistic model. And this picture that I show you here is what we believe is the correct relationship between all these classes. So all the regions here we think that are non-empty. But so far, we have not been able to prove that any of those regions is actually non-empty. For all that we know, P space could be equal to P. It would be really very surprising, but we so far have not been able to prove that this is not the case. Okay, so what we expect from quantum computers is that, of course, they are able to solve all the problems that we can solve efficiently with a classical computer also efficiently, but they will also be able to solve other problems that are not efficiently solvable with a classical computer. Okay, for instance, the famous factoring problem, we think that is one of the candidates to be outside P but inside BQP. Okay, well, we know for sure that it's inside BQP, and we expect it to be outside P, although we have not been able to show. Okay, What we do not expect is that quantum computers are able to solve NP-complete problems. This is also a common misunderstanding about the theory of quantum computing. And when you read news in the papers, you sometimes read things like, well, quantum computers explore all the different possibilities in parallel, and then they can solve NP-complete problems. This is not the case. At least we have not been able to prove this, and we do not expect this to be the case. Anyway, there are many different problems outside P, inside PQP that we want to explore, and this is a very, very interesting area of research, and it's related to the question that I was asking at the beginning of the lecture. What can quantum computers really do? Okay, any question up to this point? Okay, I was planning to do a 5 minutes break, but I think I'm running out of time. I'm a little behind my schedule, so I will continue if there is no question. Okay, so now we have seen the definition of quantum computing, what we can expect quantum computers to solve. Let me talk briefly about the hardware of quantum computers. I won't spend much time in this because I'm no expert in the field. I work mainly in quantum algorithms. And also because I have told you the focus of the course will be on developing quantum algorithms, on the practical side of quantum computing. But of course, this is a very, very interesting field of research. And it is interesting to know that there are many different technologies that are being explored in order to construct quantum computers. For instance, the computers that we will be using and the computers that have been used by Google to achieve quantum supremacy use the superconducting technology, okay? But there are other technologies, for instance, trapped ions or quantum dots or topological qubits or diamond vacancies or nuclear magnetic resonance that are being explored, photonic computers that are being explored in order to implement quantum computing. And each of them has pros and has cons. For instance, the supercomputing technology is probably the more mature of them all. And that is why we have these quantum computers at the IBM Quantum Experience, these quantum computers also built by other companies like D-Wave, which uses superconducting technology, or by Rigetti, or by Google, but also have problems. For instance, they need to be, the processors built with superconducting qubits need to be kept at a temperature that is very, very close to absolute zero, okay? And there are other avenues that are being explored. Here, I'm showing you some on the slides. And I think it's very healthy that we have this diverse ecosystem of technologies competing with each other. And in the end, we don't know which is the one that is going to give us scalable quantum technologies that we can use for real quantum computation. So what is a quantum computer like? One of these quantum computers that we are going to use. Probably if you have watched this popular TV series, which is called Devs, directed by Alex Garland, you have seen a depiction of a quantum computer that is very similar to the one that I'm showing here. This is one of the quantum computers from the IBM Quantum Experience. And all these cables and devices that you see here are in fact most of them part of the dilution refrigerator that is needed to keep the superconducting qubits that are in a processor, in a microprocessor, in the lowest part of the computer at a temperature that is more or less 15 millikelvins. Okay, so the quantum computer is really, or the quantum processor is really very small. It's about a square of 2 centimeters by 2 centimeters or something like that. And we need all these to control the qubits in the processor and also to keep it very, very, very cold. In the Devs TV series, this computer or the computer that they use is always shown with all these cables and all these devices in the open. But in reality, this cylinder that we have here needs to be closed to isolate completely the computer from the environment, because all these properties, entanglement, superposition, interference are very, very fragile with this low temperature. Program before that we have many different models for quantum computation. The most popular one is the quantum circuit or quantum gate based model. And this is the one that we are going to use. And most of these programming languages are thought of to specify quantum circuits. So then what are quantum circuits? We are now beginning to start to define the elements that we will be using during these lectures. Well, from an abstract point of view, we could say that any computation, even classical computations, have three different elements. We have the input data, we have the operations, and we have the results. And these elements correspond to different elements in the quantum circuit model. First, we have the qubits, which are the elements of the quantum circuit that allows us to have information, okay, to have the data. Then we have operations, which are what we call quantum gates, and we will see that these are, from the physical point of view, unitary transformations. And these are the different transformations that we can do with the data in order to obtain results. And in order to obtain these results, we will need to perform measurements, okay? So at the end, a quantum circuit is kind of a physical experiment in which we have physical systems, which are qubits. We do some physical transformations, some quantum transformations on these qubits. And to obtain the results, we need to do measurements, okay? And what we are going to do in the rest of the lecture is to define all these elements in the simplest case, in the simplest possible case, which is when we have just one qubit, okay? Any question up to this point? No, really? So clear? Okay. Okay, so finally, what is a qubit? What is a qubit? Well, the typical way of introducing what is a qubit is to make the difference or to compare it with the classical bit. You know that the classical bit is an element that can take two different values, what we usually denote 0 or 1, okay? A qubit, different from a bit, can take an infinite number of different values. It can take values that are part 0 and part 1. This is what we usually call a superposition, okay? And from a physical point of view, a qubit could be any quantum system that is capable of being in two different states. And from a mathematical point of view, which is, since I'm a mathematician, the way I like to see this kind of thing, from a mathematical point of view, this is a vector in a vector space of dimension 2. Okay, so we have a complex vector space, a vector space in which we have the coefficients of the combinations of the vectors are complex numbers, and we have two elements in the base. We have 0 and we have 1 inside these funny little symbols that we call qubits. This is part of what is called Dirac notation for quantum physics. We also have the brass, and together they form brackets, okay? But we will work mainly with qubits. And whenever you see one of these symbols, it means that this is a vector, okay? And in fact, we have a basis of two vectors for one qubit, the two different or two distinguishable states that we can have in a qubit, which are called 0 and 1. But we can also have superpositions, combinations of these qubits. So a qubit can be in state 0, can be 100% 0, can be 100% 1, and can also be a combination of 0 and 1, okay? And this combination is given by this linear combination of the two elements in the basis with complex numbers. And the complex numbers must satisfy one property. Their absolute value or their modulus squared must add up to 1. Okay, we will see in the next slide what is the reason for these two complex numbers that we call amplitudes to have this property of adding up to 1 when we compute the absolute value squared. Okay, so the difference here is that classical bits can take values 0 or 1, and qubits can take values that are somehow intermediate. They are part 0 and part 1. This is what we call a superposition, and remember that this is one of the properties that we want to exploit when we do quantum computations. Okay, so this is the way in which we define the state, the data that is stored by a qubit. But when we want to see what is really inside the qubit, we cannot access directly the alpha and beta, the amplitudes of the state. We need to perform a measurement. And surely you know from popular depictions of quantum mechanics, because you are physicists and have studied deeply quantum mechanics, that when we perform a measurement in a quantum system, the result that we obtain is, on the one hand, random, and on the other hand, modifies the state of the system. So we can have a happy qubit which has amplitudes alpha and beta. I think somebody's trying to ask something. No? No question? Okay. So we can have a qubit that is in a superposition with parameters alpha and beta. And when we...
Alpha and beta.
Sorry, there is someone with the microphone unmuted.
The microphone was delayed.
Okay, so anybody wants to ask a question? Okay, so now I'm also unmuted. Sorry for this. Okay, so we can have a qubit which is in a superposition of 0 and 1 with coefficients with amplitudes alpha and beta. And when we measure, we obtain either 0 or 1. We do not obtain more information about alpha and beta. We obtain one of the two values at random. And the probability of obtaining 0 is alpha, the modulus of alpha squared, and the probability of obtaining beta is exactly the modulus of beta squared. And this is the reason why we imposed that alpha squared plus beta squared should add up to 1, because these are probabilities, and of course the probability cannot be greater than 1. Okay, so when we perform a measurement of a qubit in order to see what is going on with the qubit, what is stored in the qubit, we obtain either 0 or 1 randomly with these probabilities. And moreover, once that we measure the qubit and we obtain, for instance, 0, what happens is that if we immediately measure learning more about alpha and beta, okay? And this will be important, for instance, when we study the BB84 protocol. We will see in more detail what this means in that context, okay? Another interesting property of the qubits, and in fact of quantum systems in general, is that we cannot copy, happily copy this information. You can think, okay, I have a qubit in a certain state. I want to know what is alpha, what is beta. So if I measure, I destroy the information about alpha and beta because I obtain 0 or I obtain 1. So let's make a lot of copies before I measure the qubit, and then I can repeatedly measure all these copies to obtain more information, at least about the squared modulus of alpha and the squared modulus of beta. Sorry. Well, unfortunately, this is not possible. There is a quite simple to prove theorem, which is called the no cloning theorem, and we will prove it probably next week, which states that if we do not know the state of a qubit, we cannot make an independent copy of the state of that qubit, okay? So that prevents us from that strategy of trying to make different copies and measuring all of them, okay? So this is about the data stored in a qubit, what is the information stored in a qubit somehow, how we obtain part of that information, how we observe the state of a qubit, and the other element in the quantum circuits that I mentioned is the transformations, the quantum gates, okay? So, well, before that, well, I will go to the transformations, and maybe then I will go back to the block sphere, because I'm really a little behind in the schedule, and I prefer to explain about quantum circuits, and we will see this interpretation later, okay? So, what are these quantum gates? What are these transformations? Well, those of you that know quantum mechanics surely know that the evolution of a quantum system, of an isolated quantum system, is given by the famous Schrödinger equation, okay? I won't enter in details here of how to solve this equation. This is beyond the scope of this course. But what is interesting for us, what we need to know is that in the case of quantum circuits, this Hamiltonian that we are applying here is independent of time in general, and the solutions that we obtain for the evolution of the state are given by matrices. Okay, so we have qubits, which are vectors, and now we have transformations, which are matrices, and we are going to multiply these matrices times the vector to obtain the new state of the system, the new state of the qubit. And the important property about these transformations that are the solution to Schrödinger's equation is that they are matrices that we call unitary matrices. And this means that they always have an inverse, and the inverse is given by the conjugate transpose of the matrix, or the dagger of the matrix, or the dagger of the matrix, okay? We obtain the inverse just by transposing the matrix and changing all the elements in the matrix, all the complex numbers in the matrix, to its conjugate. And in that way, you will obtain the inverse of the matrix. So one thing that is particular from the way in which we do transformations in quantum circuits is that we always have an inverse for any operation. This is something that, again, does not happen in classical computation, because we have operations such as logical gates, such as, for instance, AND, or XOR, or NAND, which are not reversible. If I have an AND of 2 bits, if the 2 bits are 0, 0, 0, 1, 1, 0, the result will always be 0. And if I want to go back from the information of the result from the 0 to the initial, to the inputs of the gate, I cannot do that. But in quantum gates, in quantum circuits, we always have a transformation which is the inverse of the one that we have just performed. Okay, so this is a little bit different, but it's not an impediment. It was shown back in the 50s and 60s of the 20th century that reversible computing is equivalent with a small overhead, with adding not many new wires and gates to the circuit, to classical digital Boolean computation. Okay, so anything that we can do with classical non-reversible computation, we can also do with reversible computation. And one way to prove that is, for instance, to study this gate that I have here, which is called the Fredkin gate. And another important implication of this reversibility of computation is that it was discovered back in the 60s, something that is called Landauer's principle. And this states that the only operations that need to dissipate energy, to consume, to waste energy, the only information processing operations that need to consume energy are those that are irreversible. So in principle, if we can do reversible computing, we could decrease the consumption of our computational devices as much as we want. Okay, I won't enter into much details about this, but this is an interesting consequence. Okay, so now we know about qubits. Now we know about how to measure the value of a qubit and what we obtain and what happens to the state of the qubit. And we know about the transformations. Okay, the transformations are unitary matrices, and the way in which we transform the state of a qubit to a new one by one of these physical operations, which are quantum gates, is by multiplying the matrix times the vector. If we have a qubit, which is a superposition of 0 and 1 with amplitudes alpha and beta, we can represent the qubit as a column vector, okay, with the two amplitudes alpha and beta. And we can represent a 1 qubit gate, a transformation, a unitary transformation that acts on just 1 qubit, as a unitary matrix of size 2 by 2. This matrix, of course, is unitary, so its inverse is obtained by this formula here, obtaining the conjugate transpose. Okay, and the action of this gate, the new qubit that we obtain, the state of the new qubit that we obtain when we apply this quantum gate, is given by the multiplication of the matrix times the vector. And this is mathematically solid in the sense that unitary matrices keep the norm of the vectors. In fact, they keep the inner product in the Hilbert space, and in particular, the new coefficients, the new amplitudes that we obtain, again, their modulus squared will add up to 1. So this is a transformation that is permissible in quantum mechanics, because again we have a valid qubit after we do this transformation. But from a mathematical point of view, we do not need to care about the physical implementation behind. We can think only about vectors that represent the states of the qubits, and then multiplication by matrices. Okay, so what are some of the gates that are important in quantum circuits? The first of them all is the NOT gate, okay, which is given by this transformation, by this matrix here. You can check easily that this matrix is unitary indeed. You compute its conjugate transpose, which is X again itself. And if you compute the product of the two matrices, you obtain the identity. And you can see by just multiplying by the representation of vectors 0 and 1, 0 will be the vector with component 1 on the upper part and 0 on the lower part. You can easily compute that when you multiply 0 by this matrix, you obtain 1. And when you multiply 1, when you apply the X gate to 1, you obtain 0. This is why we call this matrix or this gate the NOT gate, because it changes 0 into 1 and 1 into 0, okay? Exactly like the classical NOT gate. Another important gate is the SET gate. The SET gate transforms 0 into 0 and 1 into -1, okay? And this is another matrix that we will use a lot. So it's useful to try to remember these matrices. Again, you can check that this matrix is, of course, unitary, because we will start using them in protocols, in algorithms next week, okay? But before we do that, I want to show you how these work in a quantum circuit, okay? In a very simple way, what happens with these gates when we apply them to a quantum state. Okay, I will do that in a minute. Another important gate that we will use all the time is what we call the Hadamard gate or H gate. In this case, the matrix, as you see, is a little bit more complicated. Again, you can check easily that this is a unitary matrix. And the action here begins to be a little bit more interesting. Up to this point, well, the NOT gate just changes 0 into 1, 1 into 0. The SET gate introduces minus in the 1 and leaves the 0 unchanged. But this matrix, this unitary transformation, this gate, takes 0 into a superposition and takes 1 into a different superposition, okay? So now we have a new state of a qubit that has amplitudes 1 over the square root of 2, 1 over the square root of 2. And of course, when we square these values, we obtain 1, okay? We obtain 1/2 plus 1/2, which is 1. And what is interesting about these states is that they are an equal superposition of 0 and 1. If we now measure this state with 50 probability, we are going to obtain 0. With 50 probability, we are going to obtain 1. And as we have mentioned, from that point on, the state of the qubit will be either 0 or 1, okay? The result that we have obtained. These states are very, very important. And for that reason, they have special names, okay? So ket plus and ket minus, or simply plus and the states plus and minus, are these equal superpositions of 0 and 1. In this case, with a plus, with an amplitude of 1 over the square root of 2 in front of 1. In the case of minus, with amplitude minus 1 over the square root of 2 as amplitude of 1, okay? You can think that, well, these states are more or less the same, in the sense that if we measure them, we will obtain probability 50% of 0, probability 50% of 1, because even in the case of the state minus, when you square minus 1 over 2, you obtain 1/2, okay? But one thing that we need to take into account is that these minus signs, when we have superpositions of states, when we do not have a minus that is affecting the whole state, can be very important, and will be, in fact, we will see that probably next week or the following. They are the source of the interference that we will use in many of our algorithms, okay? So these states are completely different. In fact, they are orthogonal in the Hilbert space, although the probabilities of obtaining 0 or 1 with either of them are exactly the same, okay? So I want to show you now, let me change the screen that I'm sharing, I want to show you now these gates in action. Okay, I'm going to go to one of the links that I have prepared for you on the Indico page, which is for the Quirk simulator. Okay, and in the Quirk simulator, we are going to see, I don't know if it is big enough, I'll make it bigger. We are going to see that now, well, here we have 2 qubits, and we have many different gates to choose from. So far, we have only seen the set, the X or NOT gate, and the H gate, okay? But we will study more of them in a minute, okay? And we can use this simulator to see what is the effect of the gates, of combinations of gates over the states of the qubits in our system, okay? So here you see that these 2 different qubits are initialized to value 0. This is something that happens with all quantum computers that are based on the circuit model. They all start to 0, and then we can apply gates. So we can see here a representation of what will happen with this qubit. This is the block sphere representation. I think I will explain this representation next week because I want to be able to get into the IBM Quantum Experience and run some experiments there. So I will not explain in detail what this means, but here you have the probability of obtaining 1 when we measure this qubit. And of course, this is 0% because this is completely in state 0. There is no superposition of 1. There is no amplitude for 1 here. But if I change the state to 1 applying the X gate, now we have 100% chance of, when measuring, obtaining 1, okay? I can see also the amplitudes of this qubit by using this module, this visualization module here, which is the amplitude display. And here we have the part that corresponds to 0, the part that corresponds to 1. In this case, after applying the X gate, we have obtained state 1. So the amplitude for 1 is exactly 1, okay? If I remove this, now the amplitude for 0 is 1 and the amplitude for 1 is 0. If I apply the H gate, now I obtain an equal superposition of 0 and 1. You see here that the amplitude, what it's called here, the value of the amplitude is 0.7 something, okay? This is the value, the decimal value of 1 over the square root of 2. And you see here that the magnitude squared is 50%, okay? This means that when we measure, we can see it here also, when we measure this state, we will obtain either 0 or 1 with 50% probability, okay? And this is, in fact, let me change again to my slides. I will skip some, I will go directly to the first circuit that I wanted to run on the IBM quantum computer, because otherwise I think we are not going to have time today. So we have seen that if we apply the H gate to the initial state of a qubit, which is 0, and we perform a measurement, what we obtain after applying the H gate is this plus state, this equal superposition of 0 and 1. And when we measure, we are going to obtain a random bit with exactly 50% probability each. In fact, in practice, because this would be by itself very useful, this is a perfect way of generating randomness. This is something we have been working here at CERN Open Lab in collaboration with different companies, for instance, with Cambridge Quantum Computing and with Random Power. This is something very, very important in practice, the possibility of generating random perfect bits that can be used for simulations, can be used for cryptography, can be used for many things. In fact, in actual quantum hardware, there are defects, there are errors, there is noise, and the probability of obtaining 50%, obtaining 0, 1 is not exactly 50%. There is some bias. You can then use other techniques like randomness extraction, but well, at least theoretically, this circuit will allow us to generate perfect random bits. Okay, and this is the first very easy example that I want to run on the IBM Quantum Experience. Okay, so let me change again, and I will go to the browser again, and here you have this other link to the IBM Quantum Experience. Okay, so please now go to this web page, and here, well, I'm already logged in, so let me see if I can how can I log out here? Okay, let me open.
On the right side, on the top right.
Maybe it's
This little human.
Okay, thank you. Okay, so what you will see is this welcome page, and here you can sign up, okay? And then please provide your data. You will receive a confirmation email, and you can enter the system, okay? I'm going to enter now again to log in again, and I will give you a couple of minutes to sign up, okay? And I will be explaining the different elements that we have here. This is the IBM Quantum Experience that I've been telling you about the whole time. And this is where we can run different quantum algorithms on quantum simulators and on quantum hardware, okay? So here on the right, you will see what IBM called your backends, which are the different devices that you can have access to. Probably you will see less computers here because I'm in the research program, and I have access to some other computers that are not available for the free accounts, but you will see some real devices and some simulators, okay? And you will see information about the number of qubits of these devices and something that IBM calls the quantum volume, which is a figure of merit, a metric that tries to measure the quality of the whole computer, okay? So it's not only about the number of qubits, but also about the quality of the fidelity of the gates and other features of the device itself. Okay, so you see here that I have several different 5-qubit devices. I also have 1-qubit device, and I also have a simulator. Okay, the easiest way to run a program, a circuit here, is to go to the circuit inspector or to the circuit editor, okay, or circuit composer as IBM calls it. And here you will see that we have something similar. I don't know if in black this is really very easy to see. I will make it a little bit bigger. Maybe this is better. Okay, you see here that we have different qubits. Okay, and here we also have classical bits in order to measure the result of the operations and the measurements that we perform on the qubits. Okay, so I'm going to work with just 1 qubit, as we did in the case of the Quirk simulator and in the circuit that I showed in the slide. So with this bean icon, I'm going to remove this qubit and this qubit, and now we have only 1 qubit and 1 classical bit. Okay, and here I can again, just by dragging the gate, start to describe, to define my circuit, okay? And I'm going to define the circuit with just a Hadamard gate and a measurement, okay? And we already have here some information. Here we have information about what is going to be the result when we run this circuit, and with 50% probability we are going to obtain state 0, with 50% probability we are going to obtain state 1. Here we have information about what IBM calls the Q sphere, which is related to the block sphere that I will explain next week. I expected to do it today, but well, it's better to leave it for the next lecture. This is not exactly the block sphere, but is related to it. And we also have information about the amplitudes, okay? Here, again, you see the amplitude, which is 1 over the square root of 2, okay? You have more information here in this code editor, which is an equivalent program that we can use also to run this circuit. To run this circuit, we can just compose it on the editor, and this is very convenient for very small circuits like this one. But in other cases, we want to be able to do it in a more comfortable way, especially if we have very big circuits and we need to add a lot of gates. Okay, so we can do this with a language which is called QASM, or quantum assembly, which is a language which is defined in order to specify the different elements of the circuit. It's very, very easy to understand. This is a direct correspondence with the elements that we have here in the composer. So we declare one qubit, what is called a quantum register, a classical register. Both of them are of size 1. And then we apply the gate H to the first qubit, which is the only one that we have. And then we measure the qubit and store the result in the classical bit. Okay. This is one way of specifying circuits. This is a bit better than the composer for big circuits, but this is not the best way. The best way is when you have very complicated circuits or very complicated algorithms to do this in Qiskit, which is the language, the Python library or framework defined by IBM in order to construct quantum algorithms. And here you see that in this case, since it is very simple, the structure follows almost the one that we have on the QASM file. We import some packages, some modules, and then we declare a quantum register, a classical register, both of size 1. We construct the circuit from these quantum and classical registers, and then we apply the H gate and the measure. Okay, so far so good. This is more or less the same. Okay, we will see in a minute what we can do with Qiskit that is not possible to do so easily with the composer or with the QASM code. Okay, but for now, let me show you how to run this simple circuit that we have here. Here you have run settings. These run settings allow you to choose in which device of the ones of the backends that you have available you want to run your quantum circuit. So here, if I click this list, I see that I have many different quantum devices. I have a simulator, I have a quantum computer of just 1 qubit, and many others of different sizes. Okay, since I'm only using 1 qubit, I'm going to select this 1 qubit quantum computer. Now we have here a very important parameter, which is the number of repetitions of shots that we want of this circuit. So when this circuit is run on the actual quantum computer, it's going to be run several times. Remember that this is a probabilistic way of computing. So the result that we obtain when we run the circuit once is probably not the same that we obtain if we run the circuit again. And in the general case, we want to run the circuits many times to compute some statistics over the results that we obtain. Okay, so we can here specify the number of repetitions up to 8,192, which is the maximum. Here you can also see the job limit. I have 5 jobs remaining. This is the number of jobs that I can send at the same time. Okay, when one of these jobs finishes, I can again send a new job. There is no limit in the total number of circuits that I run. There is only a limit in the number of circuits that I'm running at the same time. Okay, so to do it more quickly, first I'm going to run on the IBM Quantum simulator. Okay, and to run, I just click on this button here, run on IBM Quantum simulator. Okay, so now my job is being submitted to the Quantum simulator. Depending on how many jobs are now in the queue, I can see here that in the Quantum simulator now there are 4 jobs. I will have to wait more or less. I can check the results or the pending jobs that I have. It should appear here soon if it has not finished yet. Or I can go again to the circuit composer. Well, this is taking some time, maybe because people are now signing up for the IBM experience, and this is going a little bit slow. Okay, let me see if I can reload this. Okay, so this is something I knew it could happen, because there were many people interested in following the lectures, and if many people are accessing at once, probably the system is not prepared to support so many concurrent users. I don't know if you on the Zoom session are able to run the jobs. Have you been able? Anyone? Or are you also experiencing problems with this?
Yes,
Also,
yes. I think
we are kind of stuck.
Okay,
yeah.
okay, no problem, no problem. I have a plan B. Okay, I have a plan B. I told you that, well, eventually this should be, well, here at least my circuit is transpiling, which means that it is being transformed from this specification in either the composer or the Quantum code or the Qiskit code to the real unitary gates that are going to take place in the quantum computer. Okay, so this is a good sign. It will run eventually, but in the meantime, since this seems to be quite slow, I'm going to show you how to run Qiskit programs in a Jupyter notebook to do something similar to this. Okay, and for that, well, I would like to do it on the here on the part of the quantum experience that allows us to run Jupyter notebooks, but I'm afraid I need to do it on my computer with the local installation of the Jupyter notebook. So let me find where I have this. This should be here. No, this should be here. Okay. So I think now you can see my screen, my browser with a Jupyter notebook. Okay, maybe this is too big. Yes. Okay. Okay, I'll take that as a yes. So I have prepared for you this this Jupyter notebook that eventually you will be able to upload to the IBM Quantum Experience and run there. Or if you have a local installation of both the Jupyter server and of Qiskit, it's not very difficult. You can find information online, or I can explain it next week if you want me to. Well, if you have that local installation, you can run it now. If not, you will have to wait until the IBM Quantum Experience is accessible again. But I will show you what things you can do with Qiskit that are more useful and more comfortable than just doing the circuit or explaining or specifying the circuit with the editor, with the composer, or with the Quasm code. Okay, so here in Jupyter, we have cells with either text, code, or images. Here, this is a code cell, and I can run it just by clicking here the button for run, or I can press Shift and Enter. And then in this case, I'm going to import from Qiskit the different modules that I need. Okay. Now, what I'm going to do is something similar to what we saw in the Quantum Experience as an equivalent to the Quasm code. I'm going to define a circuit, a quantum circuit, which has 1 qubit and 1 classical bit for the measurement. Okay. This is a little bit different to the code that we saw before, because in this case, we do not give names to the registers. Since we only have 1 qubit and 1 classical bit, we don't need names. You can do it in the other way too. And then we apply the H gate and the measure, okay? And this range 1 is, well, because usually we have more qubits, and we here write, for instance, 5 if we have 5 qubits, and we measured all the 5 qubits in all the 5 registers, classical registers, at the same time. So I can run this, and with this draw option, I can see here a depiction of my circuit. Okay, I can also very easily obtain the Quasm code, which is the one that we saw in the Quantum Experience before, and then we can run this circuit in different devices. Okay, locally with the installation that I have access to what is called the Quasm simulator, which is a simulator that supports measurements, and then at the end it will show me the probability or the number of times that I have obtained each of the different possibilities. In this case, I'm going to run it 1024 times, and since I expect the probability to be more or less 50-50, I expect to obtain 0 more or less 112 times, and 1 more or less 112 times. Okay, so in this case it was 500 against 524. Okay, and here we can see the histogram of these probabilities. Okay, so this is one possibility, to execute locally in a simulator that performs measurements. Another possibility that is very interesting, and this is exclusive to simulators, is to compute the final state of the vector and see the final state of the vector. When I was explaining about the information that is stored in a qubit, I told you that you cannot access directly the amplitudes of the qubit in a real quantum system. You have no access because you need to perform measurements. But if you simulate the behavior of the system, what you can do is just to perform in a sort of way the multiplication of the vector and the matrix and see what is the final vector that you obtain. Okay, so in this case, I run the state vector simulator. Notice that I need to change a little bit the circuit, because now the state vector simulator does not support measurements, because I want the whole state before I measure it. Okay, and what I obtain are exactly the amplitudes for 0 and for 1 in this equal superposition that we have created with the Hadamard. Another very interesting possibility that we can do in Qiskit is compute the unitary transformation that is being performed by a complete circuit. In this case, it's very easy because we know that we are using only the H gate. So the transformation that we are going to do must be the matrix associated to the H gate, okay? But in a general case, if I have a more complex circuit, I can have many different gates interacting with each other, and I want to see what is the final transformation that I'm doing. I can compute that with the unitary simulator. Notice that I only need to change here the backend. I get this new backend and I execute with this new backend. In this case, I don't need to change the circuit because again, for the unitary simulator, we don't support measurements. Okay, so if I run this, I obtain this matrix, which is exactly the matrix associated to the Hadamard gate. Okay, so this is what I can do locally with my installation. This is run on my computer. Okay. What can I do if I access the IBM Quantum Experience from my local installation? This is something that, of course, you can also do on the IBM Quantum Experience with the Jupyter Notebook server, but you can also do with your local installation. Okay. What we need to do is first to load the account. You will see. Maybe I can go back to the Quantum here and show you that in the information here you have a token. This is an identifier that you can use to run from your computer programs in the quantum devices or in the quantum simulators of the IBM Quantum Experience. So you need to copy this token, and in your code you need to save the account. The instruction that you need to use is similar to this one, is IBM Q.save account, and here you use your token. Okay, and with this, once you need to do that only once, and then you can load the account as many times as you want. And when you do that, you can access now remotely the IBM Quantum Experience. Of course, this is going to be slow again because, well, I guess many people are trying to access the IBM Quantum Experience. And here what I'm doing is first retrieving all the different backends that I can use to run my jobs. Okay, and here you see that there is some information, the name of the backend, the version, if it is operational, the number of jobs that are in the queue, and some other information. Okay, I can now select one of them. For instance, I'm going to select the IBM Quantum simulator. So again, this is a simulator which supports measurements, but this is located in the IBM Quantum Experience infrastructure. So this supports up to 32 qubits, which is something that probably your laptop or desktop is not so comfortable running. Okay, and I can send my job. I can send my job exactly as I did from the interface of the IBM Quantum Experience. And with this order here, I'm sending the job, and I should get some information when this enters the queue here about what is the status of my job, how many jobs are before it on the queue, if it is going to run soon, and things like that. Okay. Of course, I don't expect this to finish soon because the system is clearly overloaded. Okay, but eventually this job will finish and I will obtain the results. Again, here I'm printing the different frequencies of the results of 0 and 1 and plotting the history. Okay, and what I do next in the next cell, you can do this on your own whenever the quantum experience is not so overloaded. What I'm doing here is now requesting to run on an actual quantum computer. Okay, so remember that this quantum computer is the one that has only 1 qubit, but for this circuit is enough. And again, notice that I don't need to change much. I only need to change the backend that I'm using, and with the same instruction, I can execute the job directly on quantum hardware. And then what I had prepared here is a comparison between the results obtained with the quantum simulator and with the device in order to see whether they agree or not. But I'm sorry, I don't think I will be able to show you this today, but I guess this is probably easy for you to do on your own, and we can discuss this next week if you have problems. So I think I'm now on time. I don't know if there are any questions. There are some topics that I wanted to cover today that unfortunately I wasn't able to, but I prefer to explain less things and these things to explain them clearly. And surely we will have time to go over these other topics in the next lecture. So I don't know if you have any question, any comment. I hope that you can run these programs on your own. Maybe later on the quantum experience will be more responsive. I don't know how many people are following this on the webcast, so probably many. And for you here on the Zoom call, I don't know if there is something that you want to ask or comment or something. No? Okay, so thank you very much. It was a big pleasure to have you on board for this lecture. I hope to see you next week. You have the links again on the Indico page, and remember that it will be again at 10:30 Geneva time on Friday.
Yeah, thank you very much, Elias. It was very interesting. We are receiving excellent feedback from this first session. There were more than 1,500 unique IPs connected, so I'm not surprised that the IBM Quantum Experience is suffering some problems. We will try to contact them in the future to organize maybe some special slot, see what we can do.
That would be great.
Thank you very much.
Thank you.
See you all at the next session.
Bye.